Hello, welcome back. This is our fourth video on the cardiovascular system. And in this video, we're really going to be looking at what is happening within the capillaries. How do we move nutrients, whether that be oxygen or anything else, from within the capillaries into the tissues? And the flip side of that is, how do we get waste material, metabolic material that's collecting within the tissue into the capillaries so that the body can begin the process of getting rid of the waste material? And so to understand that, we have to understand some terminology first. And so these three terms that you see before you are key in understanding this process of how we move materials between the capillaries and the tissues that the capillaries are embedded within. Bulk flow, right, that is the total movement of fluid between the tissues and the capillaries. Or another way of looking at that is, it's the total movement of fluid that's being exchanged within the blood and the IF, or the interstitial fluid. And so one of the things that you need to kind of keep in mind here is that you're not just simply moving things like oxygen and carbon dioxide. You're not just moving those types of materials. What you're actually moving here is water. And very often, that water is what is carrying whatever it is that you're transporting back and forth across the various membranes. And so this idea of bulk flow is, as water is now moving from within the capillaries into the interstitial tissue, or as the water is moving from the interstitial tissue or the fluid into the capillaries, what's driving that movement? And the simple answer to that is, it's a pressure gradient. Right? If the pressure of the blood being exerted onto the capillaries is greater than the pressure of the interstitial fluid pushing back on the capillary, material is going to flow out. Right? So let me draw a little schematic here for you to try to rein that in for you. Right? So here's my capillary. Here's my pressure inside the capillary. Right, so I have a high pressure inside of the capillary. If that pressure is greater than the pressure being pushed back, smaller arrow. And so this area over here, this would be the interstitial area, right, where this would be where the tissue is. Right, so if the force exerted by the blood on the capillary is greater than the force of the interstitial fluid pushing back on the capillary, then your net result is fluid is going to move out. Fluid is going to move out. Fluid is going to move out. All right. And that movement is what we define as filtration. That movement is what we define as filtration. Filtration happens at the arterial end. It is at the arterial end within the capillaries where we see pressure exerted by the blood on the capillary being greater than the pressure of the interstitial fluid pushing back on the capillary. At the venous end, at the thoroughfare end of the capillary, what we see, I'm going to continue my capillary out. So this is the arterial end. This is going to be the venous end. So what we see over here is the pressure of the blood being exerted on the capillary is less than the force of the interstitial fluid being exerted on the capillary. Right, notice my arrows are now reversed. My arrows are bigger outside and my arrows are smaller on the inside. And what that's going to lead to is the movement of fluid into the capillary, or the process is known as absorption. And so absorption is the movement of fluid now back into the capillary. And that always happens at the venous end. So filtration is happening at the arterial end. Absorption is happening at the venous end. And this here is kind of what that looks like. So what you're seeing here is, again, here is the arterial end. Here's the venous end right here. Right? This here, of course, would be that thoroughfare area, right, where the blood is passing through. You can see that the arrow going out of the arterial end of the capillary is greater than the arrows, or larger than the arrows of the interstitial fluid moving into the capillaries. All right? The reason why these arrows are insinuating that the pressure of or the direction of the movement is moving out is because, I'm going to jot this up here, the pressure exerted by the blood on the capillary is greater than the pressure of the interstitial fluid on the capillary. And so the pressure gradient favors filtration. The pressure gradient favors filtration. On the flip side of that, absorption is happening at the venous end because this script is flipped. Right? Here, the pressure exerted by the blood on the capillary is lower than the pressure of the interstitial fluid pressing on the capillary, which is greater. And that is going to favor absorption. That is going to favor absorption. So this is another view of that same process. This is another view of that same process. You can see on If you look, I'm going to draw an arrow through here. Right about there. Right about there. You can see these little arrows are all pointing outward over here. And so if you look, this is the arterial end. We would expect the pressure within these capillaries to be greater than the pressure in the surrounding interstitial fluid. And so we are favoring filtration on this side. But on this side, notice that the arrows now are moving inward. Arrows are all moving inward with the exception of a couple over here, but the arrows are all moving inward, and this is because the pressure, we've now lost all of this fluid from within the blood. That's going to reduce the overall pressure. Pressure within the interstitial fluid is now increasing. Right? Or maybe it's not increasing, maybe now it's just the fact that it hasn't changed, but it's now greater than the pressure within the vessel because the vessel has lost the fluid. And so this is going to now favor, this is now movement in, and this is going to favor absorption. Okay, so that's what this here is showing. The science behind this, or the physiology behind this, again, comes back to this idea of hydrostatic pressure. All right. The pressure that, or the fluid is applying a pressure on the capillary that is greater at the arterial end than what it is at the venous end. And so, if you wanted to calculate that hydrostatic pressure, under normal conditions at the arterial end, hydrostatic pressure within the capillary. Hydrostatic pressure within the capillary is 30 millimeters of mercury. Within the interstitial tissue, and this is what I mean by the interstitial space, all right, so there is, let me draw this again here. Here's your arterial. This is your capillary. You usually have a little bit of a space that separates out the capillary from the interstitial tissue. Right? And that here is what is being referred to as the interstitial space. And the interstitial space, functions as almost like a, for lack of a better example, it's like a wet t-shirt contest. All right. Your body would be the capillary. Right? The t-shirt would be the interstitial space, and then the surrounding area around you would be the interstitial tissue. Right? And so that t-shirt gets wet, and what does it do? It suctions to you. Right? And then you gotta sit there and you gotta pull it, and you let go, and it goes right back to you again. It suctions back into you. All right. That interstitial space does the same thing. It kind of adheres to the capillary to hold it in place within the tissue. Well, that's got a sucking effect within the capillary. All right. And so where you see -3 millimeters of mercury, right, that is actually what I define as being a pulling pressure. In other words, because it's suctioned to the capillary, it's increasing the pull outward. It's increasing the pull outward. And so that total hydrostatic pressure within the capillary is measured at being 33 millimeters of mercury. Right? So you've got a hydrostatic pressure. You've got a pressure pushing against the wall of the capillary that is equal to 33 millimeters of mercury. Why is that important? Well, let's look at a couple other numbers here. There's another pressure within the capillary called the colloid osmotic pressure. Now, this is both within the capillary and within the interstitial tissue. And it's the pressure that is created within the capillary and or within the interstitial fluid by the presence of proteins. So proteins are generally too large. Think of the lymphatic system. All right. Those proteins were too large to go in to leave the lymphatic fluid, to leave the interstitial tissue and move into the capillary bed. So they very often got filtered out. Same thing here. The proteins that are within the capillaries are too large to cross the membranes, the endothelial membrane of the capillary. And so they don't leave, they stay. Right? They stay. Think of your globulins, your albumins. Think of your immunoglobulins. Think of white blood cells. Think of red blood cells. All of these things are all protein based, and they're too large to cross the endothelial membrane. So those proteins have a pressure that they've created, and that's a pressure of resistance. Right? That's a pressure of resistance. And so blood has a colloid osmotic pressure of 28 millimeters of mercury. Well, the interstitial fluid also has a colloid osmotic pressure, which is 8 millimeters. Right? Now, why the difference? Well, the capillary is a lot smaller of an area, so any proteins that are in there are going to have a greater impact because they're being contained in a smaller area. The interstitial tissue and the interstitial fluid is a much greater area, and so those proteins can be spread out more, so they have less of an overall impact on the pressure. Right? But because they are at best, because they are opposing forces, in other words, the proteins in the blood are pressing one way and resisting movement, and the proteins within the interstitial tissue is pushing down in the opposite direction, and again resisting any kind of movement. You subtract the two of them to get the total difference in the colloid osmotic pressure. So the colloid osmotic pressure within the vessel is 28 millimeters of mercury. The colloid osmotic pressure within the interstitial tissue is 8 millimeters of mercury. The difference in that is 20 millimeters of mercury, and we define that as being the onconic pressure. The onconic pressure. And so the onconic pressure is 20 millimeters of mercury. Now here's the thing, and this is going to become evident in a little bit. Because these proteins are too large to move across any of the membranes, this onconic pressure is consistent throughout the capillaries. This will not change. Right? This will not change. Your hydrostatic pressure is going to change. Right? Your hydrostatic pressure is going to change as you go from the arterial end to the venous end, but colloid osmotic pressure, or this idea of this onconic pressure, is going to be stable. Right? It's not going to change as it moves through the vessel. And so, with using the onconic pressure as well as the hydrostatic pressure, we can then go ahead and start looking at rates of filtration and absorption. And so net filtration pressure is the difference between the hydrostatic pressure and the onconic pressure. And it is, and this is something I have yet to fix in this PowerPoint. I really need to do this. The net filtration pressure is a positive 13 millimeters of mercury out of the capillary. All right. This here is not a negative sign. It's a bullet. Think of it like being a bullet. And the same thing here. This is a bullet here. All right. So this is really a positive 13 millimeters of mercury out. So here's our capillary. All right. Once again, remember what I drew before. All right. Big arrow in the capillary, little arrow in the interstitial fluid. All right. The net filtration pressure that is happening within our capillary beds is equal to 13 millimeters of mercury. And it's favoring filtration. In other words, it's favoring that fluid moving out of the capillary. All right, and the reason for that is because the hydrostatic pressure is greater than the onconic pressure. Remember, under a normal circumstance, hydrostatic pressure is 33 millimeters of mercury, and we're going to subtract that from the onconic pressure, which is 13 millimeters of mercury, which equals NFP, net filtration pressure. NFP is going to equal 13. I'm sorry, this is 20. My mistake. All right, so the onconic pressure is 20. Some of you are probably yelling that at your computer screens. 33 minus 20 equals 13 millimeters of mercury. Equals 13 millimeters of mercury. That is on the arterial end. Net reabsorption is going to be the difference in the hydrostatic pressure in the venous end and the onconic pressure, which we know does not change. Right, which we know that does not change. And so we'll look at this here in a couple minutes as well, and kind of look at how this is all changing on the venous end. But that is what we would define as reabsorption. All right, that's what we would define as being reabsorption. The difference between the hydrostatic pressure and the onconic pressure on the venous end is typically 7 millimeters of mercury, but that pressure is being favored inward. And so let's look at that. Oh, let's not look at that yet. Let's talk a little bit about Starling's forces here first, and then we're going to look at the other numbers. So what I just explained, right, what I just explained about net filtration pressure and net reabsorption pressure, and what the environment is that is favoring both the net filtration and the net reabsorption, is what we summarize as being Starling's forces. All right, so Starling's forces is literally the equation of net filtration pressure is equal to hydrostatic pressure minus onconic pressure. That is what Starling's forces are summarizing. So it's a set of equations that allows us to calculate out what exactly is happening within the capillary beds. All right. And this is what it looks like. This here is a diagram that you're going to want to make sure that you know and that you understand. All right. Because I will ask a series of questions on this specific diagram on the lecture exam. All of the numbers will be removed, and you will simply just have the diagram with none of the numbers or wording available to you. Right? But again, let's look at what's happening at the arterial end. Here's the arterial end. Right? Again, blood hydrostatic pressure. Right? Blood hydrostatic pressure is 30, right, out, plus the interstitial hydrostatic pressure, the pressure caused by the fluid, right, kind of on that interstitial space, causing a suction. Right? It's sealing itself to it. Right? So that's plus 3. And so this is where we're getting that 33 millimeters of pressure out, net hydrostatic pressure, right, out. We know that the colloid osmotic pressure, all right, is 20, and that's going to be ultimately favoring movement in. All right. And so the net filtration out, as we've already talked about and shown, is 13 millimeters of mercury. Well, how did we get 7 millimeters of mercury for net reabsorption? Well, if we look at the venous end, these numbers are broken down for you. The blood hydrostatic pressure at the venous end inside of the capillary drops to 10 millimeters of mercury. Coming in, it was 30. That drops to 10. Right? What accounts for that drop? A loss of fluid during filtration. So as we're filtering, we're losing fluid. As we are filtering, we are losing fluid this way. And as you lose that fluid, pressure decreases. Pressure decreases within the capillary. Right, so that's what's accounting for that drop towards the venous end of the blood hydrostatic pressure. Interstitial pressure is still going to be the same. And so this time we're now adding 10 plus 3, which is 13. So your net hydrostatic pressure at the venous end of the capillary is 13 millimeters of mercury. But remember what I said. Colloid osmotic pressure doesn't change. Colloid osmotic pressure does not change. And so that onconic pressure is still 20 millimeters of mercury. And again, that's facing inward. Right? That's facing inward, or at least the direction of the movement is into the capillary beds. And so you, once again, you take 13, subtract it from 20, and we get negative 7, or in other words, moving into the capillary. And so that's 7, the net reabsorptive pressure is 7 millimeters of mercury. Inches, and that IN that you see there, no, that's not inches, that's just, scratch that. Ignore that. And so that's the 7 millimeters of mercury moving in to the capillary. All right. And so I'm going to leave you there now to kind of go back through and try to get a better understanding of what's happening here with the movement. And again, answer up your questions and jot down your questions that you may have as you move through. And I'll catch you on the flip side.